Hi, everyone. My name is Kennedi White. I'm a rising junior physics major, math and English double minor at Howard University. And with my co-authors, I looked at the variation of the moon's solar-induced hydrogen cycle during a solar storm. So like y'all have heard multiple times today, and I hope y'all understand, water is a very important resource. And it's very important for our current and future lunar exploration projects. And that is why we wanted to try and understand how solar wind implementation produces water, hydroxyl, and other water products on the moon, as like I said before, current and future lunar exploration projects. We were also trying to see and understand how the variation of surface hydroxyl water and other water products and volatile transports to cold traps usually located at the poles. So this project was derived from a Frel et al. Paper, which you could see in my references, that looked at the enhanced lunar exosphere during a solar storm due to a coronal mass ejection passage that entered the Earth-Moon system back in 1989, specifically during the time of April 29th to May 7th. They were focusing on sputtered atoms, and in our project and what I will be speaking on today, we will be focusing in on hydrogen atom content on the surface and the escape of hydrogen molecules through the exosphere. And this is looking at the same solar storm that was looked at in the Frel et al. Paper. So we used a Monte Carlo simulation model. And with the model, we put an input of omnidata of the flux during the solar storm. And through this, we tracked the diffusion of hydrogen molecules onto the surface and the diffusion of hydrogen molecules out of the exosphere. And then as an output from the model, we collected images and models of the surface, hydrogen content, and of the escape of the hydroxyl molecule from the exosphere. And we're going to be looking at those in the results. So right here in this GIF, we see multiple images of the lunar surface from the beginning, at the moment the coronal mass ejection entered the Earth-Moon system on April 29th to when it ended in May 7th. And this period right here when the black areas, which is representing the daytime of the moon, is stopped, is May 1st through May 7th, which is May 1st through May 5th, which is the exact time that the solar storm was occurring. There were significant amounts of changes that we could witness on Earth, in fact, during May 1st through the 7th, with key on the maximum, which is on May 4th. We saw a significant change in the moon phases, noting that it went from a waning crescent to a waxing crescent significantly faster than it should be. And we also noticed some high concentrations and the abundance of hydrogen protons on the surface, focusing on the equator, which is the middle portion at 0 latitude, and at the poles, which is at the bottom and top of the graphs. We were focusing more on the equator area and equating outwards as opposed to the poles, because the poles weren't at a steady state and the equator was, so we were focusing in there. So when we looked a little further at the surface content of the hydrogen content on the surface of the moon, we noticed that at maximum, which like I said before, was around May 3rd and May 4th, there was a significant concentration of hydrogen concentrated at the equator. And this is shown by the lighter blue color towards the middle area at the daytime. You also see a large concentration of it at the poles, as seen in like yellowish look appearance. We also noticed that there was a second spike which occurred on the 4th, which was after the moon had exited the Earth's magnetotail, which had a spike in the surface content almost exclusively at the lunar poles. We can't necessarily, well, we didn't take measurements at this though, because like I said, the poles wasn't necessarily at a steady state and we couldn't necessarily conclude that the amount of hydrogen found there would stay there. And looking at the exosphere at the exact same time at the same phase angle, we noticed that at the spike, there was a large concentration of hydrogen molecules escaping at that time, as seen by the dark red areas, not only at the day side of the moon, which is focusing on the inside of the black region, but also on the dark side of the moon, featured on the far left and far rights of those areas. And immediately after the storm had left, almost all of the hydrogen molecules had left the lunar exosphere, as seen in the bottom plot, with it being a much darker shade of blue, with some portions of the hydrogen still being on the dark side of the moon. So in conclusion, what we had found on the surface is that the low latitude hydrogen content nearly tripled, especially along the evening terminator, which if I go back, you could see it, which will be on y'all's far right, with the morning terminator being on y'all's far left. And this persisted until the following sunrise, following sunrise of the following day after the storm had concluded, with a solar wind flux at 25 times the nominal values. We also saw that in the exosphere, the hydrogen molecule exosphere density nearly tripled, with it subsequently decreasing as the storm left the Earth-Moon system. And we noted that the hydrogen molecules responded quickly to the varying solar flux because of the thermal escape in the wee hours of the morning, and of course, most of it staying and eventually leaving as the day transfers. With our future implications, we are noticing that during solar storms, hydrogen molecules may be more easily observable. With the current mass spectrometers we have in the UV instruments, it's currently, well, we know currently that we can't really observe hydrogen molecules at its nominal conditions. So hopefully looking at more solar storms, we'll be able to measure them. And we were also looking at discovering and understanding what happens to hydrogen molecules transported to the coldest PSRs, and specifically if it will be able to stick and be chemically converted to more complex species. Specifically in our case, what we are interested in is water, because the water that I've been speaking on during this presentation has been molecular water. I'd like to acknowledge the LEADER project, which derived this project in my university. And at the third references is the paper that this project derived from. Thank you.
All right, I believe we have time for one question. Do we have any questions online or in the room? All right, we've got one in the room.
Hi, Parvati Prem, APL. Good talk, Kennedy. Do you have a sense of like how often do these solar storms that cause a detectable change in the exosphere occur?
Can you repeat the last bit, please?
Yeah, so how frequently do solar storms like this one occur? So like this was in 1989.
So I can't give you a concrete answer because it's kind of erratic, but I can tell you that there have been more solar storms that have happened since 1989. I was just talking to Dr. Tucker on Tuesday about a more recent one happened in like 2017 that we were going to look at, because that was another thing that we were trying to ingest. The whole focus was on an increase in hydrogen due to the solar storm, and we can't really rely on them happening as often as we'd want to in order for them to be reliable. So we've just been kind of focusing on, well, we're about to focus on this one in 2017, but after that, how long the hydrogen that comes stays on it, because there's no use in it coming and then leaving again from the exosphere. Yeah. Thank you.